Cool. So yeah, thanks for coming to learn about lattice-based SNARKs. If you don't know what lattices are, don't worry, I'm going to explain that. But I mean, you probably get an idea. It's something to defend against quantum computers. And quantum computers, of course, I'm not going to give an intro of quantum computers here, but I'd be interested in what people think about quantum computers. They were always a thing for a very long time, but people started panicking sort of not so long ago. I think the first thing I remember was maybe in 2016. The NSA released this memo that said, if you're on the move to deprecate or to move to ECC, elliptic curve cryptography, then maybe don't do that and move directly to post-quantum cryptography. It was something like that, and everybody was wondering like why we're doing this, and are quantum computers really a threat? And I think there's this paper from Koblitz and Menezes called a riddle wrapped into an enigma, or vice versa. And they try to understand like what could have happened. Are quantum computers really, is that really what they have in mind? Or so a lot of people were wondering, okay, what the fuck is happening? And then a bunch of academics started, trying to create more, not FUD, but more hype around quantum computers. And they started this whole thing of quantum-resistant algorithms or post-quantum cryptography, which I learned recently. We're trying to move that to plausibly quantum-resistant, I think, because it's not clear if it's actually, secure against quantum computers, but we think they are secure. So, I guess the NIST, if you don't know the NIST, it's an American organization. They organized this competition, I don't know what year, to sort of come up with, and they say it's not a competition, but it really looks like a competition. And people basically came up with a bunch of schemes that were supposed to be quantum resistant. And there was like cryptanalysis, people were trying to break them, and so on. And so they came up with a bunch of interesting things. Some stuff were broken, but lattices were part of a number of schemes were lattice-based. But before I get too much into lattice, I thought it would be interesting to get maybe do a little poll on who here thinks that quantum computers are going to break cryptography. Maybe show of hand. Do you think quantum computers are going to be here to break cryptography in 5 years? One person? How about 10 years? Oh, okay. Like almost the whole room. So does anybody here think quantum computers are not gonna ever be a thing that can break cryptography? Nobody? Okay. So I guess I used to be in that camp for a long time. I don't really know where I am today. When I was writing my book, Real World Cryptography, I wrote a chapter in post-quantum cryptography. And so I remember trying to quote or read about what physicists were thinking about. I was like, I'm not a physicist, so probably I'm not the right person to really understand these things. What do physicists think about that? And it sounded like a lot of physicists didn't really think there were like a lot of problems that were kind of unsolvable, like there were a lot of errors that you had to correct, and at scale it was not possible. And so there were a lot of doubts, whereas in the cryptography community there was a lot of hype, and of course the incentives are a bit different. People want to get grants and these kind of things. So it wasn't clear exactly if, at the time when I was reading this thing, it wasn't clear if it was going to happen. It sounds like you guys disagree with me, maybe I agree with you guys now. In any case, the NSA and the governments are on a different sort of threat model, where for them they're really scared of adversaries that are recording the web and recording all traffic, and maybe they have documents that they want to keep private for the next 50 years or something like that. And so in this case, you have to plan for like algorithms that will withstand the test of time for like the next 50 years or whatever is their time scale. So the sort of good news is that symmetric algorithms and asymmetric algorithms are not impacted in the same way. So symmetric cryptography, think hash functions, encryption, authentication, like MACs, all these things are pretty much safe, or at least we don't know good algorithms to break them. There are some algorithms, but basically if we increase the parameters, for example, if you use SHA-512 instead of SHA-256, or AES-256 instead of AES-128, these kind of things, then it seems like things are secure. So asymmetric is, we don't have to worry too much about it. Asymmetric, so think signatures, key exchanges, public key encryption, SNARKs. I don't know if SNARKs really, I guess SNARKs you could put it there as well. All of these things are basically broken. You can sort of increase the parameters, but it becomes so unrealistic that it's not very nice. And so people are mostly focusing on these algorithms when they're trying to find these, plausibly quantum secure algorithms. Okay, does that make sense? So I guess I'm gonna focus mostly on lattices and on SNARKs because that's what I like. And so I started reading about that basically to give that talk, and I realized when I started reading about it that there's many things happening already in lattice-based SNARKs. There's a lot of hype, and a lot of the personalities in zk are actually working on these problems. And basically, we already can see solutions to, we have solutions to like lattice-based SNARKs, but also like folding, recursion via folding is an entirely separate sort of field, and it's also booming with papers and interesting proposals. So maybe I can mention that. So there's sort of the PCS or like SNARK side, we'll say, and there's the sort of a folding side. I'm not gonna really talk about folding. So if you don't know what folding is, it's really it's a way to recurse with SNARKs. And for that, there is a lattice fold that came out. Lattice fold, I think that came out last year. And this year, there's two derivative works that came out, Lattice Fold Plus and Neo. And this is by Bini and Dan Bonnet. This is by Srinath. And these are basically people that are in, that were in the SNARK field before and are trying to do folding. That were in the folding field and are doing more folding but with lattice. And I haven't looked too much into that, but just so you know, it seems like people already like these schemes a lot. It sounds like these are two orthogonal improvements that can be sort of combined. But just to quote Dan Bonnet, like he gave a talk that I was watching, and he said, that might be the first time where something that's post-quantum, quantum resistant is actually better than the non-post-quantum alternative. So it sounds like the properties of folding with lattice are already that interesting, that people are considering using them even today when we're not too scared of quantum computers. Okay, that's the last time I'm going to mention that. I'm going to focus on that side. Having said that, I also started remembering that we already have SNARKs that are post-quantum secure. So if you think of STARKs, or there's a bunch of, I don't really know, like Aurora, Ligero. There's a bunch of algorithms that people are actually using today, but with parameters that are not quantum secure. But since they only rely on hash functions, they are plausibly, quantum secure if you were to increase the parameters. It's possible that if you increase the parameters so much, it's not very performant, and so it kind of sucks. It sounds like Lattice performs already better than these hash-based algorithms, so it really seems like a very good solution. And maybe one last thing I can mention, like Lattice are sort of like homomorphic by default, so you can commit to stuff, and then you can add these commitments. And with hash functions, you cannot really add to to digest. And so usually to do folding with STARKs and like all these hash-based stuff is kind of hard. There are schemes that exist like Arc, but they're not very efficient. So Lattice are really good for that. And you're going to see that it's also really good for just building SNARKs. Yeah, does that make sense? Like Lattice, right? Lattice no more. So how do we build a SNARK with and don't worry if you don't know what a lattice is. I expect most people don't know what lattices are, but I'll explain what it is. But I just want to mention before I get into lattices that it's pretty plug and play. Today, if you look at most proof systems, you can sort of split them between a PCS, so polynomial commitment scheme, and the part above that makes use of it, usually PIOP. And so if you just replace the PCS with a post-quantum PCS or quantum-resistant PCS, then it works, right? And this is basically what SNARKs are. You can see SNARKs as like kind of like Plonk or like SNARKs, but using a hash-based PCS. That's one way to see them. So it's not always what happened. Like there was a bunch of research this year actually trying to do SNARKs with Lattice, not really taking that approach, and a bunch of them didn't. It's not that they got broken, but their security was based on some knowledge assumptions, and these knowledge assumptions got broken, so their security is not really understood. But we're lucky because in the last years, especially, I think it was from this year, there's a bunch of, this year or last year, there's a Greyhound that came out. Greyhound. It's actually based on an earlier paper. So I think maybe this is from this year, this is from last year, something like that, called LaBRADOR. And I think they had a paper called Chihuahua before that. Chihuahua. And these schemes are already pretty interesting. Like they're already very likable. So if you look at Greyhound, so it's a PCS, so plug and play. You can use it in your proof system already, and it has sublinear verifier. So sublinear verifier means that the verifier is more efficient than the thing they're trying to verify, or the thing the prover is trying to prove. So usually sublinear is something we like. So square root of n, where n is the degree of that polynomial. I think it also has sublinear proof size, let's say square root of n or something like that. And it's linear prover. So in the land of normal SNARKs or like non-post-quantum SNARKs, like we always trying to get linear provers. And we like when it's sublinear verifiers, because then we can do like folding, we can do like a bunch of recursion stuff and so on. It's not as good as something like gross 16, which is like polylogarithmic. So that's what we call succinct. So technically we cannot really call these succinct because they're just sublinear. Even though it's good, it's not the best. But so for example, Mina works on a sublinear proof system. And so today you have deployed proof systems are sublinear and we like them. The thing is, it's actually not sublinear proof because by using LaBRADOR, you get even better proof size. So I don't remember exactly what's the size of these proofs, but like concretely, you get proofs that are like around 50 kilobytes. So 50 kilobyte is kind of like, it's worse than something like gross 16, which is just 100 bytes. But compared to like hash-based schemes, which are also deployed in the wild, it's actually pretty good. And for like matching parameters, I believe Lattice-based SNARKs have like smaller proofs than hash-based schemes. Cool. Okay, so did I talk about everything I wanted to mention? I think most of that I talked about. Yeah, does that make sense? Yeah? All right. So next I want to try to introduce lattices and what they are, and then maybe I'll talk about Greyhound. So lattices. My way of thinking about lattices is to start with vector spaces, which most people are familiar with. And in vector spaces, you have vectors, and you can add vectors together, and you can scale them with a field. And so here, for example, the vector space created by these two vectors which is called the base of the vector space, is all the vectors you can create from these two vectors. And so usually you end up filling the whole space, because you can scale this vector like by 0.9. You can do whatever you want. You can add this one, or you can subtract this one. And you end up being able to create all sorts of vectors. And usually, if they are linearly independent, then you can cover the whole space. Doesn't matter too much for this explanation, but this is what vector spaces are. Now imagine that you cannot scale these vectors by any real numbers, but actually only by integers. Then you get a lattice. So a lattice is really, so if you have two vectors, for example, you can add them. Or maybe a better way to explain is to look at that vector and that vector and sort of create this mesh. And basically every point is a vector that you can create by adding these two vectors together. For example, 1 times that vector plus 2 times that vector, or like minus 1 times that vector, and so on. You always have the 0 vector. But yeah, that looks kind of ugly, but hopefully that drives the point. Does that make sense? Yeah. So yeah, vectors, we're scaling them by integers. So so far, it's just a kind of a vector space. And also I guess I can write down how you would think about it. Is the set, so lattice is the set of all the, I guess, coefficients times bi, such that ci is the ci's are in the integers. So you're just taking linear combinations of some base vectors, right? And if you have usually a way to represent this space is to have a matrix where all the b0, b1, all the vectors are the columns of that matrix, and so you would write that as bc, right? A random linear combination of the columns here. I guess it's good to get used to like writing stuff with matrices, because that's what you end up doing in the lattice world. Okay, so that doesn't matter too much. Oh, okay, hard problems. So in cryptography, we like hard problems, right? Because we want to build crypto system based on these things. Hard problems are basically things that we think are hard to solve. We're not sure, but we're pretty convinced that they're just hard to solve. Think problems like factoring, factoring numbers and stuff like that. So in lattices, there's a lot of 3-letter problems. Maybe I'll start with the SVP, the shortest vector problem. And the shortest vector problem is like given some base. So imagine these 2 vectors in my lattice. Find the shortest vector that is produced in that lattice that is not 0. And so, so maybe, I don't know, maybe here the shortest vector is here. I have no idea. And so you have like these algorithms, like LLL is a famous algorithm, to try to, given a basis, try to find the shortest vector in that. We don't care about SVP today, but just wanted to mention it. There's another one that's closely related called CVP, the closest vector problem. And that one is like, if I give you a point in the space, tell me which is the lattice point that's the closest to it. These are, does that make sense? Yeah. So finding the shortest vector, I'm just looking at you and you're frowning. So just to recap, the shortest vector in this space, SVP, that's not 0. And CVP is, I give you a point that's not on the lattice, find the closest point on that lattice. And these are what we call worst case hard problems. And they're called worst case because they're not always hard to solve. If I just generate a lattice, it might be that it's easy to solve. You can think of like factoring as sort of like that. Whoops. And that's why like in RSA, like I'll produce a number that has two big factors, and we know that this is hard to solve, but not every number is hard to factor, right? So worst case, we don't like too much. And by the way, here in RSA, knowing the factorization is a trapdoor that allows you to create different proof systems. There's the same kind of notion in these problems here, but we don't, for what I'm going to explain, we don't care about that because we're not using these trapdoors. But yeah, worst case, just to go back, worst case, we don't really like that because, I mean, there's different reasons, but my understanding is that if you generate uniformly random scenarios, then it's not clear if they're going to be secure, and you might end up in your protocol where you end up with like some lattice or something like that, and it happens that it's not a worst case lattice, and so it kind of sucks. So what we like is average case problems. Oh. Average case problems, and so that's the one I'm going to use in Greyhound, or they use in Greyhound. And the famous one, well, the one I'm going to use is called SIS, and it means short integer solution. And so the idea here is that given a base, find a vector here. So let's call it, I don't know, let's call it x. Find a vector such that you have a zero vector, actually, modulo some q. So that's SIS, short integer solution. It's an average case problem, meaning that if I give you like some random matrix here, or lattice, it will be hard for you to find an x. And by the way, x has to be short. I forgot that. Whoop. So it's going to be hard to find an x that's not zero, right? Zero is a trivial solution. That's and by the way, remember that notation, it just means random linear combination of the vectors, right? So it's hard to find a solution, a random linear combination that gives you the zero vector. Such that, and that's important, and that's actually really annoying, such that that vector has a small norm. So you can think of it as it's a small, for some definition of like small. So beta usually is a parameter that we give in a proof system or in these instances. So I'm not gonna tell you what it is. And the norm is also something you can define, and depending on the proofs, you can use different norms. But I'm not gonna define these things. Basically, just you can imagine that you can look at the vector and find the biggest entry, and for example, that would be the size of that vector. There's also variance, ring cis and module cis. Basically, here in cis, the lattice is made out of integers. In ring cis, the lattice has vectors of size 1 that are made of ring elements. And in module cis, you still have vectors, but they are ring elements. So I'm gonna open that a bit more. But spoiler alert, this is the module cis is the one that we use. So module cis, that's the problem, but everything in your lattice is a ring element. And I'm going to define for what ring. Before I move on, also I want to mention the fact that maybe people were worried that cis was not the most well-studied problem. They were like, okay, SVP and CVP are pretty well-studied problem. No, we want to rely on cis, so it kind of sucks. Like the cryptanalysis has not been done or something like that. Well, it turns out that this guy called Ajtai or something like that, I don't know how to pronounce it, proved that if you can break cis, so if you play a game with let's imagine you're the attacker, and I play a game with you, and I send you like these instances, and you can find these vectors, you can break it with good results. Like on average, you're better than random. then I can use your algorithm to break worst case instances of these problems. And so that means that the nice thing is it means that either this thing is secure because SVP and CVP are secure, you know. So CC is secure thanks to that, because we reduce the security to that. Or someone finds a way to break CIS. And so I heard someone say that, I can't remember who. In this case, then mathematics wins. And so we found a breakthrough and a way to advance our understanding of these schemes. Okay, so I was explaining hard problems. There were a bunch of hard problems. Some are worst case hard problems. Some are average case hard problems. And this is the MSIS one is the one we're going to use, right? Yeah, any questions so far?
Is Q there? Should we think of that as like a large prime? Or?
Yeah. Actually, it's a smaller. You will see, but it's like size 2 to the 32. Okay. So the nice thing also is that you have. So apparently we like rings because we can have like smaller. We can use smaller primes, and we can efficiently model them. I guess with computers, and I'm not exactly sure why it's fast, but apparently it's fast. Maybe someone knows.
It's fast because ring elements they're encoded as like integer vectors, but they're actually meant to represent the coefficients of polynomials, and you can do fast Fourier transforms to combine those polynomials in ways that you otherwise wouldn't be able to do in just like normal sys or.
Right.
And it also takes the key size from on the order of like you go from very, very, very large matrix keys that are like so large that it's hard to transfer to like things that are much, much smaller, especially once you get to modules.
Oh yeah, so I guess what you're saying is because we have these big ring elements, we can reduce the size of the matrix. Is that what you're saying?
You can reduce the size of the matrix, and also the multiplications that you can do between ring elements are faster.
Right. So it's
importantly, it depends on like the structure of this ring. So
right.
It turns out like the polynomial modulus that you use for this particular choice of ring gives you this like nice splitting structure.
So I guess I can.
You can use these like number theoretic transforms.
You have to use very specific. It's like n squared plus 1.
Okay, so we.
It's like x to the n plus 1, and n is a power of 2.
Yeah.
So this is called like a cyclotomic ring.
Right. So we like rings because entity, right? So the number theoretic transform. So maybe maybe that's a good segue to talk about the ring that we're using. I don't want to talk too much about the ring because it's kind of confusing. But yeah, the ring that we're using is like the polynomial ring with this like 2 to the 32, around 2 to the 32 prime, divided by some polynomial. Actually, I can write it. X to the, I think usually they use 64. And that's, I believe we call that anti-cyclotomic because it's +1 instead of -1. But yeah, I think, the whole point is that you can, it's not an irreducible polynomial, and so you can factor that polynomial in a bunch of polynomials, and I guess that's why entity works. But let's not get too much into that. Let's just imagine that we have a ring, and you can see these things as polynomials, where the coefficients of these polynomials are in ZQ, so they're around 2 to the 32, and there's these polynomials are of degree 63, so less than 64. So they have 64 coefficients. So that's the. All right. So am I done here with everything? By the way, how much time did I take? 30 minutes? All right. Yeah. Any Any other question or comment on? All right, let's get rid of folding. So I'm gonna keep this Ajtai guy up here because what we're gonna use is, oh, and I forgot to mention, but we're gonna use Ajtai commitments, and you're gonna see that these commitments, since we're not using any trapdoor, we're gonna use these matrices that are public and can be generated, I guess, in a public way, so there's no trusted setup. So these schemes are also transparent, which also is something we like. Like SNARKs and like these kind of schemes, but not like Plonk or not like KZG and these things. Okay, and so I take commitments. So basically, you take a matrix. So let's call it. So that's your, like B. Like you have a bunch of vectors, and these are, vectors with ring elements as entries. So you can think of these polynomials as entries. It doesn't really matter for what I'm going to explain, but just so you know. And you multiply that with your vector, and it's going to give you a commitment. And that works, or that's secure, only if S has a small norm. As we said earlier, like these vectors have to be short for that to work. So that's an Ajtai commitment. The nice thing you can already see is that this is homomorphic, and so that's why folding works so well, and that's why a bunch of these schemes work so well. So, okay, so these are the commitments.
So is A a fixed Ajtai matrix, or is like?
Yeah, so basically you can see that as a public parameter. From what I understand, you don't need to store it in memory. You can have like seeds that will generate the matrix. So it's that nice. So yeah, apparently it's pretty. So I'm imagining that maybe you just raise a number to some powers or something like that. But yeah.
Is A just uniformly random integers, or is it picked from some distribution?
Yeah, I don't know. I would assume it's just uniformly random, but.
Yeah, so A is typically just going to be generated using like an extendable output, like add function. And yeah, you use like some way of like sampling coefficients.
So XOF, is that what you meant, or like extended output function?
Yeah, yeah.
All right. So you just use these massive hash functions, or?
Yeah, exactly.
All right. So I guess this guy we don't need anymore. These are Ajtai commitments. Oh. Okay, so now we're back at looking at things that are a bit easier to understand, right? This is a pretty easy commitment scheme. Maybe one thing I can mention here also is that these matrices A, what people will do is that often they'll use pretty wide matrices with very short, I think they short rank and high multiplicities. And so if the vector you're trying to commit is pretty large, you end up with a pretty small commitment. Right? So the commitments are usually much smaller than what you're trying to commit. Because you have many such vectors, but they're small. Right? They don't have too many entries. And that's sort of, I guess that's one of the reasons things get quite small and you can do folding and all these things. All right, so I'm going to try to explain Greyhound. The last time I tried to explain it didn't go so well, so let's see how it goes. But the first trick they use in Greyhound, and probably I'm not going to talk about LaBRADOR too much, but the first trick they use is that imagine you want to evaluate. We're talking about PCS, right? Polynomial commitment schemes. We're trying to commit to a polynomial and evaluate it. So what we're going to do is we're going to take some polynomial f, and you have to imagine it's like f0 plus f1x plus f2 x squared plus f3 x cubed, and so on. And you can also see that as like, yeah, let me continue here actually. x4, just to make the example. You can sort of see that as you can chunk your polynomial, And you can see the first part, and then whatever comes next, I don't know, I'm gonna call that f prime 0 of x maybe. And all that stuff here is gonna be x4 times another polynomial, and x8 times another polynomial, etc. And if this one, I mean, you can see it's f4 plus f5x, 7x cubed. So they all of degree 3. So you can just chunk your polynomial, right? You can, and so if you do that, you can put all the coefficients in a matrix. And this is a trick I've seen, like Ligero has that, I think Aurora has that, or different schemes in the past. And you can just write your coefficients in that matrix. Okay, maybe I'm not gonna write all of them. And if you write your coefficient in that matrix, you can also notice that I can multiply it on that side by a vector of evaluation. So let's say I want to evaluate at some point x. I can have a vector that looks like that on the left side, and I can have a vector that looks like that on the right side. Right? And that should give you, if f of x is equals to y, that should give you y. So that's the first trick, is to think about evaluating a polynomial as two matrix multiplications, where you encoded the coefficients of the polynomial in that matrix, and you have two vectors on each side for the evaluations. If you don't believe me, you can try to do it, and it works. But yeah. So now what we're going to do is that we're going to look at these vectors, and we're going to commit to them. So these are going to be the vectors we're going to commit to. So we're going to get a bunch of commitments. The problem is that these coefficients, they're not necessarily small. Remember I said earlier that Ajtai commitments, they only are secure if the thing you're committing is small. So we can't really commit them. We can't really commit these vectors right away, right? So another trick that they end up using in all these papers, I guess, is that you decompose all of these coefficients in some base. So you can sort of imagine that as a binary decomposition, if you want. You don't have to do it in binary, but in some base. And so you get like a much longer vector of like the decomposition of f0, the decomposition of f1, and so on. And then if you would like multiply it with if it was like binary decomposition, you would have to multiply it with I don't know, maybe like a vector like that, like something that keeps repeating the powers of the base. So, yeah, does that make sense? Yeah?
I'm curious what you mean when you say you can't do it unless it's small. Is that like it doesn't work within the scheme? Or?
So you can do it, but it's not binding. And so meaning that...
it's not a commitment scheme because it's not binding.
Well, it's a commitment scheme that's not binding. So you can find other solution. I don't know how efficient it is, but that's the theory. It's like you can find other solution that will... other openings for the same commitment, right? Oh yeah. So it's simple.
What's the motivation to do the binary?
So again, we can only commit to vectors that are short, so have small values. So we have to make these values small, right? So yeah, that's a bit annoying. So maybe I'm not gonna talk too much about that, but you have to imagine that every time we commit, we have to decompose the values in some basis. And so every time we want to use them, we have to recompose them. And so we have to multiply stuff with these kind of things. So if you read the papers, you see a lot of decomposition, recomposition, and stuff like that. And for folding, it's a bit annoying sometimes. Well, actually, I'm not going to mention it. All right. Okay, so how can I go from here? Okay, so let's say that I've decomposed all of this stuff. What I get is a bunch of commitments. What can I? Okay, these are the SI. I'm going to call that S1, S2, S3, S4 in my example. I'm going to commit to these things. And so the commitment to my polynomial is going to be basically, well, I'm going to call them like that. Yeah. T1, T2, T3, T4. Right? Where T1 is A times S1, which is A times decompose. What is that vector called? F prime 0? Maybe? Oh. Does that make sense, that notation?
A stays constant. You don't need to regenerate A for each commitment, correct?
Right, right. For some reason I don't understand, they will use different matrices for different types of commitments in the scheme. I think that's just for domain separation, but there might be another reason. But at least for committing to polynomials, you always use that matrix A. Okay, so where can I go? Okay, I'll go here.
One question.
Huh?
So S1 it's not the column, it's just F0, the decomposition?
So S1 is the decomposed column here.
Okay.
So F0 is here, has been decomposed. F1 is here, has been decomposed.
So up there, S1 decomposes F0, or is it F0, F1, F2?
Well, this is prime, just because I use prime to say this thing here.
Oh, okay.
So this is the, let's call it, it's a bad notation.
Gotcha.
Hopefully we don't use that anymore. Yeah, we're good. Yeah. Okay, so how does it work? So the broken scheme where we can start is that the prover will basically compute that part first, the left part first. We'll send that left part to the verifier, and the verifier will then compute the right part themselves. And the whole idea when you sort of encode your matrix like that is that, you know, you can have this side be the square root, this side be the square root. So your proofs are going to be of size square root because of that, and the work that you do is going to be square root because of the size of everything you do is basically one of the side of that matrix, or at least that's how I think about it. Okay, so you got it. The prover will do the left multiplication first, and then the verifier does the right multiplication after. So what happens that the prover does W equals, how can we call this? Oh yeah, they actually, in the paper, they call it A and B, right? A transpose B. So here we can call A T times our matrix, or yeah. What are the names? Oh, maybe to avoid using these, I can also use S. I can say recompose, recomp. They call it G actually. Maybe I should use the notation of the paper. G, S1, S2, S3, S4. So, oh yeah, I like arrows better, but. So this G basically is recomposing, is making this matrix here that's decomposed, it's bringing it back to that form. I could also like omit it, and we just have to remember that this is what's happening. But I can also put it here. So I send that as the prover. The verifier takes W, this, and just does multiply it with this, with B. So dot product. I guess if you don't know, the dot product is just you take the first entry. You take the first entry of this one times this one plus this times this plus this times this plus this times this, right? That's a dot product. And this should give you y. That's the evaluation of f, right? We have f of x equals y. Yeah, that makes sense, right? The problem is that we don't know if, I should do that. The problem here is that we don't know if W was correctly computed, right? We have no idea that this multiplication here that the prover did was correct. So I guess that's the second trick I'm going to explain, or the third trick. I don't know how many tricks I've explained. This is, I guess, a trick. The composition stuff is a trick. So let's say third trick is that they do this kind of thing that I'm trying to think about it in terms of what I learned about other proof systems in the past. And in other proof systems, you have this thing called Schwarz-Zippel, the Schwarz-Zippel lemma, where instead of checking that two polynomials are equal at every point in a domain, you just check that they're equal at some random point. And you do that either in the clear, like you evaluate these polynomials at these 2 points and you check that, or hidden in commitments. But here they're not doing that, but they're doing something that sort of looks like that, where basically here instead of sending W, they will they send W, but the verifier will send some challenges. So it's not an evaluation point, but it's I guess a vector of challenges. And then the prover will send something called Z, which will help the verifier check that this was computed correctly at a random linear combination. Instead of an opening, an evaluation of something, they're going to check that at a random linear combination. So let's see how it works, and maybe we can think about it. And maybe I'll write that there. So Z is a, be helpful to see the paper right now, but is C, or let's put it this way, is a random linear combination of the SI. So you're looking at the SI here, and you're taking a random linear combination, all right? And so they do W, what do they do? So I remember one side is AZ. So if you do AZ, what this gives you is basically, what does AZ gives you? So you get CI. So on that side, I think that's the check they're doing. W is this thing. Oh, that's not it. What am I? Up. Nobody has the paper on them. So you take a challenge of these things, and then you definitely have to use the AI. These are using SI. Oh no, these are using, oh yeah, these are using SI. Is this TI or? Oh yeah, no, I got it. This, I was thinking of the verification of. So I mean, we can also think about it. But basically, you have a random linear combination of the, no, that's not. Okay, let's look at the paper. I don't want to think. Thanks. C times W is equals to A. Yeah, I think that's correct. Thank you. So if you think about it, it should be correct. So basically what you're gonna get here is a multiplication of the A here with the SI, but you have the challenges are involved. And here you already have the computation that the prover did, but you're getting the challenges in that computation. And you can try to think about it. Every time I try to think about it, I get confused. But it's random linear combination with your challenges of vectors. This thing is only true if Z is computed correctly. So you have another check you need to do. Okay, let's think about that one. So I think if you do A times Z, it should give you some of these commitments. I guess you can check the paper again. Yeah. So if you commit to Z, basically, that should give you that should commit this part, and since you have the commitments, it should work. I don't have a better, yeah. Thanks for confirming. I don't have a better explanation of this, but basically, if you think about it, it works. And this check tells you Z was computed correctly, and if Z is computed correctly, then this check tells you that W, the left multiplication was done correctly. All right, I managed to do that. Of course, there might be some like decomposition and recomposition that needs to happen, but I'm kind of ignoring this. Now there's a few more changes that you can add to that, but you can sort of see a simple version of the protocol as this thing. Does that make sense? What I explained, I guess. Yeah.
You still have to check the shortness of the witness, right?
Right. So yeah, you need to check that Z is short as well. Right. Oh, and W as well. Right. W is not short, but so actually that's, yeah. So that's something I don't really need to explain it, but later you're gonna have to make sure that these things are short for some reason. But here these things are not short yet, I guess. Like for now they're not short, right? Like I haven't made the challenge space small, I guess, for now. Okay, but I'm gonna have to explain that next. Any other questions?
So that's publicly known?
Which one?
X squared.
Yeah, this is, so the verifier is trying to evaluate that polynomial that is committed. And so they will have to compute that B vector, right? They're doing that themselves. Like they're multiplying this thing W by that themselves, so they have to know X to compute that vector.
And so, like, getting W is...
Oh, and in that check also, right? They have A. So they need to know A. So they know X, right?
It's hiding, but you were saying that I could have made up something else. I could later claim something else, so it wasn't binding until I did this thing.
What I said earlier was that when the prover sends you the result of the left multiplication,
yeah,
you should not trust that thing.
Okay. Until you go through this.
Until you do these checks. And you can only trust that this was computed correctly after doing this check at some like random linear combination using these challenges. So these challenges that we sent here, right? This is the verifier. This is the prover. Does that make sense? Yeah.
Could you justify exactly why it's hiding?
Oh, it's not hiding.
It's not hiding.
Yeah, we don't care about hiding. I guess there are ways to make it hiding, but like as usual, it's always like let's think about things without hiding things, and maybe at the end let's think about it. Yeah. Cool. So now I'm trying to think how I can bridge this to LaBRADOR. So the full protocol is basically a bit more complex. There's one, or actually maybe before I talk about the full protocol, I can talk about that. Oh no, there's one more thing I can talk about. Usually you don't want to have a bunch of commitments, the T1, T2, T3, T4 of all the columns here. So they have this notion of inner commitments and outer commitments. It's not very important, and maybe I'm gonna skip that. I mean, of course it is important to make the proof small and everything, but not to understand the protocol. But you can imagine that this is a vector that's, that doesn't have short entries, so we can actually decompose that. We can concatenate that, or create a vector, decompose that, and we can commit to that again, and obtain a short commitment of all of these commitments. So in the protocol, that's what they do, and so when they evaluate things, they have to actually open the commitment of all these commitments. So if you look at the paper, you might get confused because I didn't put that in the protocol. And they also do. Okay, now I'm going to talk about LaBRADOR. Okay, I'm gonna move on. So the way, if you look at these operations that are happening, you notice that we're just doing a bunch of dot products, and we're doing a bunch of dot products with some values that we know, and some values that the sender, the prover has sent to us. So here the W is something that was sent to us. The Z is something that was sent to us. And presumably the TIs is something that was sent to us because I told you about that order commitment. So the prover is sending us a bunch of stuff. So W, Z, and also openings to these entries here. And so that's what takes room in the proof size. We could sort of stop here and just accept the fact that we have a proof of size around square root of n, the degree of the polynomial, but we want to do things better, so we want to use LaBRADOR and compress that and get better proof size. So what we do is we look at LaBRADOR, and I'm running out of space, but LaBRADOR, so basically LaBRADOR is this thing called a principal relation of LaBRADOR. LaBRADOR. And that relation is, I'm going to try to remember it. F of S0, bunch of vectors, bunch of short vectors. So if you, well, actually, let me write the entire thing. I think it's something like that. And if someone looks at the paper, they can tell me. Plus, all right. Yeah. So can you guys read that, actually? So we have a function that takes a bunch of short vectors, and they do something here with them, like there's a dot product between these short vectors, and actually we don't care about that because Greyhound doesn't use that. And then they do a bunch of dot products with some fixed vectors and the short vectors that we have, and then they subtract this B vector. And so,
just to be clear from a notation perspective, this SI, is this SI the same as the SI that is in our functional notation here?
Yeah, let's use SI prime if you want.
Okay, so it's just like different.
Yeah, this is a good comment actually. I'm writing a blog post and I actually use SI prime to make sure it's different. So now we're really talking about LaBRADOR, right? We're taking an intermission, talking about LaBRADOR. We're ignoring everything else that we've seen before. So LaBRADOR gives us a prover verifier scheme that basically, if you know, the prover can convince a verifier that they know a bunch of short vectors, these SIs prime, I guess, such that this thing here is equal to the 0 vector, right? Equals to the 0 vector. So that's the proof system that LaBRADOR gives you. Initially, when LaBRADOR came out, they were like, okay, we're going to use that thing to reduce R1CS to that. And then in Greyhound, they were like, you know what? If we reduce a PCS to that, then we can transform any proof system into a post-quantum system. But LaBRADOR didn't do a PCS. Initially, they just reduced R1CS to this thing. And so, yeah, does that make sense? You can see that as the interface of the scheme. And if you look inside LaBRADOR, basically, to verify that, they end up doing a bunch of things that look exactly like that, but with smaller SI. And so they sort of recurse until you have SIs that are very small, and then you can send that, and the verifier will actually check that equation on the small SIs. So if you know bulletproof or these kind of things, it's sort of similar. But I'm not gonna talk about LaBRADOR. This is the only thing I'm gonna say. This is the interface of LaBRADOR. And when you kind of squint your eyes, you can sort of see the same interface on our side. We're doing a bunch of dot products. And I mean, we are doing a bunch of dot products. The only problem that we have is that the things that we're sending that are using the dot products are not small. So that was the earlier comment. But we're almost to the point where we have something that looks like this relation, and so we could just give it, instead of sending this thing as part of the proof, we could just give it to LaBRADOR, and we wouldn't have to send them in the proof. And so the proof size would be reduced. Does that make sense? My way of thinking about that? Maybe it's a bit confusing.
So given like the smallest, right? Supposing you have two, I guess, small vectors that are sufficiently small, what is like the sort of counterfactual difference with like a smaller vector than one smaller vector than another? What does that do to the scheme as a result? Is it more or less hard?
You mean if they're not small, or?
No. Supposing that you have two S's that are sufficiently small, but
right.
one is smaller than the other.
Oh.
Does that?
I think that I don't think it changes anything. I think as long as you're
under a threshold.
Yeah. Defined. Maybe the smaller you are, the more secure you are, but I'm not sure. Yeah. Okay. Some Lattice experts here. But yeah. I think next what I can explain is how they end up making these vectors small. But it's kind of gruesome to explain that actually. I can sort of give the intuition and stop there. Yeah, how about I do that? Yeah. So the way they make W small is pretty easy. They commit to it. So there's another, they take another matrix. I think that's the domain separation part. Maybe you could have a scheme that's broken where you just use A, but here we're going to use D. They commit to W. So decomposition of W, not W, but I'm going to ignore that. And it gives them a commitment V. And you send the commitment V. Of course, as we saw earlier, this is like a very, very wide matrix. So V is very small compared to W. And so they send V. And you need something else. So you'll need a check that, I mean, you can see that basically you will need to open that, and that will be an SI, sort of, that would be the short stuff. So I don't know how to write it. This has been decomposed. Just imagine this has been decomposed, so it's short. And so you can see this matrix multiplication that the verifier will have to do as a bunch of dot products, right? With like di is like a row vector of d, right? that what we're doing? So and this you have to imagine that again it's decomposed. This was sent in the proof, but it's small. This is decomposed, so you don't need to send it, and we're just gonna give it to LaBRADOR. And in short, so LaBRADOR will take care of it, and we don't have to send it as part of the proof. Does that make sense? We just committed to it, we send a commitment, and we realize that we have just one more dot product to do. And since it's short, we can just delegate it to LaBRADOR. And we know LaBRADOR will not send it as part of the proof, and we'll send something smaller. So, okay, we made this thing small. As I said, the TI, well, I'm not going to talk about that. And the Z, the way they make it small, basically is to send, so remember the Z is a random linear combination of challenges of the SIs. This is not necessarily small, as you pointed out. But if you make the challenges small enough, basically this will make the Z small. That's how they do it.
When you say small and short,
Oh, I guess I meant short. I think short is a more
so
correct.
like one's about dimensionality and one's about norm.
Oh no, I don't. There's only one, and it's the norm of Z is under some threshold. Yeah. Right. And the cool thing is that these things, you have to prove that these things are short, but LaBRADOR takes care of it. Even though you don't send them in a proof, there's a way to verify that they're short. But I'm not going to explain how. This is all, we can just imagine LaBRADOR is a black box, like that, I don't need to explain it. Yeah, so yeah, at the very end, you can sort of imagine that you have a, well, you know what, I'm going to stop here. I think I'm confusing people more than, yeah, did that make sense? Yeah.
So is it just that the verifier has less choices for the CI? They have to choose CI small enough so that...
Yeah, the distribution is going to be different. Yeah.
Okay.
So I think it's just, if you look at, everything is a ring element. If I remember correctly, there's like 32 zeros. So every CI is a polynomial, right? In that polynomial ring. So a bunch of coefficients are zeros, and some coefficients are like -1, 0, and 1, like stuff like that. So we know that the SI, I think at this point the SIs are small, and so since the CI are small, it's not gonna. Yeah, I wish I could put all of that together, but it's getting very crowded. These are the intuitions, I guess. Yeah.
So just to be clear, the vector C that you're sending is a vector of randomly chosen -1s, 0s, and 1s.
This polynomial ring.
Yeah.
And yeah. Oh.
No, I was just gonna say, I think like the challenge, like maybe it's easier to think of it as like a matrix that's like basically sampled from a special distribution, and the idea is that like if you multiply the matrix by a vector that's long, okay, then the result is going to be short with negligible probability. So the verifier can catch if the vector that's being sent is long.
Yeah.
The vector that you multiply C times some S, the vector is going to be
like
long with negligible probability, right? Or short.
If the witness is actually long,
Yeah.
meaning you have like malicious prover,
Right.
and the witness is long, then if you multiply this long witness by this projection map, this like linear
But
map.
I think you're talking about a different. Aren't you talking about the the thing in LaBRADOR to like do a norm check, you just have these random projections, and then you reduce.
Yeah, this is Johnson limited chart.
Right, the JD.
This is what's going on inside LaBRADOR.
Right, in LaBRADOR. So instead of doing since we don't know these elements here, and you need to verify that they're small, the verifier sends you like these random projections.
Yeah, exactly.
And
you're talking about this. Okay.
I'm talking about
This is the outer. This is Greyhound.
These CIs, right?
Yeah. Sorry. Okay.
Right.
I thought the question was about like how you check the shortness with this random challenge.
Yeah, no, just the challenges are small here, so the result is small.
Okay.
Yeah, the verifier is trying not to grow your thing.
Yeah.
One more question?
So kind of like the idea of LaBRADOR as a black box is if you can turn all of the checks that the verifier has to do into checking that sort of relation,
Right.
then you can just use whatever machinery LaBRADOR gives you and use that.
Exactly,
And
yeah.
so it's good that we're checking like dot products here. It's good that we're checking like the A transpose G, whatever, because that can be written as like a bunch of dot products as well.
Well, that's not a check. The prover.
Oh, sorry, that's
Did that,
what
right?
the prover calculates
Right.
and sends over. You're right. It's
So the checks are, this is a check,
Yeah, that's a check.
there's 2 checks here,
Yeah.
there's this check if you commit to
Sure.
W. They're all dot product checked.
They're all
right?
dot product checks. Okay.
And the all dot product check where the part that is unknown to the verifier, because unless you send it to the verifier, are small vectors.
Okay.
Yeah?
Yeah, that makes sense.
And here it's like, it looks like this.
And just one more question, sorry.
Yeah.
About the calculation at the end to make W small, right? So you say that you generate another matrix, the prover generates another public matrix D, commits to it by multiplying D and W to get V.
Right.
Do they then are they sending V to the verifier instead of W at the top to make it smaller?
Right. So they send V, so
So we're replacing that top row or that top.
yeah, you're replacing this thing here, you're replacing it with V, so a commitment to W.
Okay.
Actually, you also need to send the evaluation. I think there might be an attack if you don't send that evaluation as well.
Yeah.
So you commit to these things, right?
Okay. So then now if you're the verifier and you have a short V and the evaluation Y.
Well, V you don't care that it's short because you have it, right?
Yes, right. Yeah, you have it. Sure.
Right.
Okay. You have V, some commitment to the value W.
Right. So here you don't send that anymore.
Yeah, exactly. So then you just and you send a challenge, and do they still need to send Z back to you or no?
So at the end here, you just enter the LaBRADOR
Okay.
protocol.
Okay.
Yeah, I think you guys got it. If you want, we can take it offline and look at the paper, and I can show you all the checks in the paper. Yeah. Oh. Cool. Should we stop here then? Yeah. Thanks. All right.